So this presentation will be about some background of AGWA. AGWA stands for the Automated Geospatial Watershed Assessment Tool, and it's really a GIS modeling tool for watershed assessment and future analysis or management analysis, considering multiple scenarios. And as Shay had said, we've been working on this for some 18, 19 years. EPA was the primary motivator for this. The Landscape Ecology Division wanted some water-related metrics to compare watersheds either through time or one against the other. So we'll be giving just a little bit of background, a little bit of model background, those models that are embedded within AGWA, some basic data requirements, some examples of some watershed assessments, and then modeling expectations that you might have for various goals. So in terms of background, AGWA is a automated GIS interface for watershed modeling, and our endpoints are hydrology, that can be total flow volume, peak rate, and then erosion and water quality with the SWOT model. And it was specifically designed for resource managers. When EPA came to us, again, they were landscape ecologists, and this made us step back, and it was difficult at first, but we had to make the model usable for non-hydrologic modeling specialists. So it was a good exercise, and we feel that's really helped build our user base. It's applicable to gauged and ungauged basins. It operates with nationally available data. Again, that was another EPA requirement saying we want to be able to apply this anywhere. And of course, your basic data is DEM, soils, and land cover. And it's typically used to investigate the impacts of land cover change. How do you identify at-risk or sensitive areas for erosion, runoff, and some water quality aspects, and assess the impacts of management, whether that be growth, post-fire analysis, application of mulch, land use change from rural to urban, that sort of thing. And it's designed to produce repeatable results for relative change analysis. And as you know, well, I mean, perhaps I'm too presumptuous here. Hydrologic models are not to the point where we can set up a model, use physically based equations, and expect to get good quantitative estimates. So if the measured peak value is, let's say, 50 cubic meters per second, my model will very unlikely be able to predict that value without very good rainfall and runoff data to calibrate the model. So when we talk about relative assessment, we're talking about percent change from a pre-management condition to a post-management condition. As I say, we've got to have good rainfall and runoff and preferably water quality data if we want to get good quantitative numbers. We still have to do a model calibration. And there's three well-established models underneath the AGWA umbrella. Kinneros 2, REM, which is the rangeland hydrology and erosion model, and that's a hill slope model embedded in Kinneros. And then SWOT, that's also a very widely used model developed by the ARS group in Temple, Texas. So just a little bit about the models. The two distributed hydrologic models are designed to address multiple scales. When we did a literature review with EPA, we didn't feel we could come up with one model that served all purposes. So SWOT's typically applied on larger basins at a daily time step. Again, SWOT is doing continual improvements, that group, and I believe they can also do hourly time steps now. It uses a concept called hydrologic response units. In other words, within a watershed or a sub-watershed, it looks at all the land or the percent of land cover that has similar soils, similar cover, and therefore you can use the same, let's say, infiltration or curve number values for that combination of soil and land cover. Kinneros is typically applied to smaller or medium-sized basins. It can be run at minute time steps. We typically run it at the resolution that we receive rainfall input data. It's physically based. It does the routing, and you can do runoff, run on, let's say from a parking lot to a field, or from, let's say, a field into a riparian buffer strip, and then into a stream. And we'll talk a little bit more about these in subsequent presentation. And REM is a model that was specifically designed for rangelands. They typically have, different properties than a cropping system, where you're plowing and tilling the field, that sort of thing. And as I say, that's embedded or becomes the hydrology and erosion engine for the hill slope components of Kinneros 2. And in terms of a kind of an abstract routing representation, so SWOT will determine sub-watersheds like the one you see here, but it doesn't make a distinction between the left and the right-hand side of the channels. It does look at an upland contributing area, and it has a built-in pseudo channel to help the timing out. Kinneros REM, on the other hand, does make a distinction between different elements on one side of the channel or the other. And again, it has an upland element and lateral contributing elements on each side and channel elements. And there's other elements, we'll talk more about those in, again, subsequent presentations. So that's some of the differences in the way the watersheds abstract a watershed, or I'm sorry, the models abstract a watershed. And our conceptual design is shown here. Basically we want to get the basic data required. Again, topography, land cover, soils, and input meteorology to drive the model. And we're going to pick an outlet on the watershed. In this case, the outlet's over in this area. We'll discretize the watershed. We will compute flow direction and flow accumulation maps to basically define the outline of the watershed. Then, depending on which model, because they discretize the watershed differently, we'll break it into modeling elements. So the light blue lines you see are channel elements, and the black lines delineate overland flow or hill slope elements that contribute to those channels. So all of those elements are intersected to the soils and the land cover. And then we do our best in terms of deriving secondary parameters like infiltration parameters, hydraulic roughness parameters, that we either go into the literature for those, we either go into experimental data. And again, these just provide a first initial guess of what these parameters are based on nationally available soils and land cover data. So if you have local information that will improve those estimates, they should be used. And we can show you how you can edit what comes out of AGWA to use that local information. So now we've got, for each one of these elements, we've got information on its geometry. So that's, its slope, contributing area. We've got information on its soils, which gives you infiltration characteristics. And then we have information on land cover that may go into the hydraulic roughness and modify the infiltration characteristics. So then we can build the input files and run the model. So in this case, we show a number of rain gauges in the black dots that'll provide input into the model. We can ingest radar data or multiple gauge data or single data. And then we can run the model and bring the model results back into the GIS to view them spatially. So any of these outputs for Kinneros, channel infiltration, plain or overland flow infiltration, runoff, sediment yield, peak flow, channel scour, sediment discharge, any of these can be color ramped and displayed on the output. So you can easily identify, and then what we're showing here is the surface runoff out of SWAT. And again, so you can visually see where the most runoff is going to be generated out of a watershed. So again, basic data requirements. We have digital elevation data at 10 meters over the US. 30 meters will work fine for larger watersheds. We've also used LiDAR in typically smaller watersheds. Soils, we can use StatsGo and Sergo where those are available. We can also use FAO soils for international applications. And from a land use standpoint, we've got the National Land Cover Data Set, or NLCD, REGAP or GAP data that's also available nationally. And we just about have the capability to ingest and use Landfire. For weather to drive the storm, you can go to the NOAA 14 website and get design storms for various return periods. And those are good for inputs to smaller watersheds. And if you get larger, you can use a point area reduction factor. You can use observed data. And again, this is critically important. If you don't get the rainfall right, you can't expect a lot of your model predictions, because that's the main thing driving the model. As I say, we also ingested National Weather Service radar rainfall estimates. And the management information is, what you have, or the sorts of things that you may anticipate the watershed is going to experience, whether it's urbanization, fire, change in management practices. And again, that's provided by the user in terms of, the watershed, and what the particular applications that may be planned for it. So this is a screenshot of some of the visualization of the results. But what we've done, and I should say Shay and the folks doing a lot of the programming, have allowed you to run 2 model runs in succession. And in other words, you can do one model run that, let's say, is pre-urbanization. You can save all the results for all of the model elements, both in time and space. And then you can do a post-urbanization model run. Again, all of the information of the elements is saved, and then you can difference the two. So that's what we see here. And again, we can pick what outputs. The streams are in these lines. So the fatter and the darker the line, the higher the magnitude, or the higher the percent difference. And here's the runoff from the hill slopes or the plains. The darker the blue, the more the runoff. And we can also, again, view the results like you might typically do in a hydrograph is, again, pre or post treatment results, compare the differences in peak rate. And again, this is a quick way to identify where things may be at higher risk from flooding or severe erosion. And here's some examples of assessments that we've done. both looking backward in terms of the upper left here for historical landscape change, and then we've got some examples of where it's been applied. Alternative futures. So there's another whole group of geographic model prediction, if you will, about how an area might grow. They use things like transportation corridors and different economic scenarios. And again, those things can be brought in and used in the model to say, here's a prediction of what this watershed might look like in 2050. And you can run that scenario, difference that with the current scenario, again, to say, what does this change do in terms of hydrology, erosion, or water quality? And again, if you want specific, these are the things we basically get out of the model that planners and land managers are typically worried about: runoff, peak rate, sedimentation, nitrogen, phosphorus with SWOT. We can look at particular subcatchments or segments and that are increased at risk. Maybe there's spawning area in a certain reach that you're particularly concerned about. And we can use these as decision support tools to say, well, if we do see a big change, what might we do to mitigate that change with another management practice? So we'll go through a simple case right now, and one of your tutorials will go through this whole process that I'm describing in these next few slides. So here's, this is the Southeast Arizona. This is the San Pedro River corridor. These are the Huachuca Mountains. So these are color IR imagery from Landsat. And this image is from 1973, and it's been classified into these categories. And this urbanized area is Fort Huachuca. It's an Army base, and the town of Sierra Vista next to it. And again, there's a repairing corridor here. So we then go to 1997 Landsat imagery that is again classified into the same categories. And we can see there's quite a large expansion in terms of urban area, both in the military base as well as ex-urban development that's scattered here and some concentrated growth here. So we're going to model that now over two scales. So we're going to use the SWOT model at the very large basin. So the US-Mexico border crosses right about here. And so we're discretizing the watershed, and this is some, I think it's about 7,000 square kilometers. And we're going to run SWOT first. So these big elements are elements for the SWOT model, as well as channel elements. And SWOT typically, again, runs and gives you things like annual water yield or seasonal water yield. So we're going to use a climate series over a 10-year period, and we're going to difference that model using the 1973 land cover and the 1997 land cover. And the darker the blue, the more annual water yield. So we can run SWOT and see, well, this area is producing a lot of runoff. And if we want to know more details about that, we can further discretize the model and apply Kinneros. So we're going to take this watershed, we're going to rediscretize it to a finer level and apply the Kinneros model with the design storm. And again, we can see where the concentrated runoff is, as well as which channels are carrying most of that runoff and or sediment. And we can see that these areas correspond to the highly urbanized areas that we saw in the classification. So it's just common sense in terms of urbanization, creating more runoff. but this gives you the spatial context in a much more detailed manner, and saying where it is, and importantly, what downstream risks might arise out of it. So a little bit about modeling expectations. From an experimentation standpoint, just getting to understand the watershed you're working with, you can accept a pretty high level of uncertainty in the model results. You're trying to understand how the watershed responds, it's important that, again, things make sense. Verification is important. From a regulatory sense, where there may be, a court case that says you're creating runoff that is affecting a downstream user, you want to have a calibrated model, which means you want more observed data. We don't always have it, but ideally you would have that. From a planning standpoint, again, you can accept a higher level of results, and you want to really look at trends. Which way is the watershed response going, up, down? So doing relative change analysis is a way to identify those trends, again, before and after, or with and without management. And here are the tutorials that you'll be working on. And again, as we showed you in the 2-day agenda, we've grouped these tutorials into separate breakout rooms. And hopefully, again, we can help each other, as well as have one of our training team answer specific questions for these. Now, again, these are all available online at the website. Show you that. So, AGWA website here, and again, it includes the documentation, software, tutorials, and pubs and presentations. And again, the tutorials, as Shay said, are coupled with the data that you need to run them. The YouTube videos also take you through most of the major steps that you would use, and again, those are not a broad range of examples, but the YouTube tutorials try to cover what the capabilities are of AGWA in different modeling scenarios. So with that, I'm done here.